Dear friends, up to now, we have seen how to implement logic gates using BJT transistors and maybe diodes. Today, we will start to this NMOS-based logic families concept. Here, NMOS-based logic families. That's what we will be seeing today. Okay. So before we start to seeing these logic gates, maybe we should talk about the MOS transistor, MOS transistor, and how it can be implemented. What are the voltage current relationship of these. So you have seen that in detail in the past. Just before we start, I want to talk about the concept first. For the BJT, the control of current, between this pin, which was emitter, and then collector and base, was achieved with N plus P and N transistor concept. And the way that we were controlling the current flow was maybe forward biasing this junction, and then reverse biasing this junction, and then electrons were coming here, electrons were coming here, and then when they reach to this region, so they swept through here in this region, and then the electrons were coming here, and then therefore that means we used to have a current through this direction, current. Okay, collector current is in this direction, and then emitters were also, some electrons were going this way. That means the current was pumped from here, I base, and then this was I emitter. Okay, so this was a originally no current is passing between N, P, N. So there are two diodes, back-to-back diodes, and that's the NMOS transistor. Okay, so that's how we obtain a transistor, back-to-back two diodes. Now, in the just roughly, the idea, for the MOS transistor, we again have back-to-back. Maybe I will explain this way. Back-to-back, there is this, let's say, N, P, N. So normally no current between here and here. So let's say one of them is source, drain. Okay, and then in order to have current between them, we don't try to turn on these junctions. Instead, there is silicon dioxide region here, and then on top of there is a conductor region, metal initially, or polysilicon. Okay, so we create a field here, and with this field, you form a channel here, and so the way that electron is going from here to here, the electron is through this leakage region. So again, we have N, P, N. So normally no current is passing. But like instead of having these turn-on junctions, we create a leakage region here. Why or how? By applying a voltage here, gate voltage. A large gate voltage will attract electrons here, and therefore that leakage is formed. Okay, so this is the general idea that maybe I thought, maybe you know it, maybe, you don't see it this way. So I thought, this could be helpful for you to understand that. So here the idea is field effect transistor. Okay, so field effect. We are creating a field, electric field, and that's how we make the transistor. And the way that this is formed, metal, oxide, and semiconductor. So metal, oxide, semiconductor stack. So that's why we call this thing MOS. So MOS field field effect transistor. Okay, and that's MOSFET. So this shows you a three-dimensional view of the device. And of course, in order to implement this, again, in the silicon surface or substrate, we need to do diffusions. So, the same way that we have seen what is done in the BJT, again, we have diffuse regions here, and then we have the source region and the drain region. Okay, so the source region and the drain region, and then this is the metal. Okay, there is an oxide, and then substrate, which is silicon. Okay, body substrate. So MOS transistor is formed. Okay, so again, this shows you a three-dimensional view of these devices. So the way that we see this transistor from the top view, this is what we draw, VLSI design. VLSI designer, can draw this. And when it's fabricated and manufactured, it is becoming a device like this. Okay, so this L-drone is the minimum that maybe can be, what it can be is reduced over the years. Okay, so this L-drone minimum, in 1990s, maybe it was like 3 micron technology. And in fact, I designed my chip during my PhD studies in this node, 3 micron CMOS, and I fabricated it myself. So, but over the years, in 2020 or so, this became much lower than 20 nanometers. Okay, I know, like, maybe 10 is okay, 10 nanometer is done, and then 7 nanometer, 5 nanometer, and it keeps going down. So so this is the L-drone. This is a little bit exaggerated here, but there is already some diffuse region here. So this is called lateral diffusion. Okay, so L effective is going to be L-drone minus 2 times LD. Okay, so we don't have to spend time on this, and then, you know, if LD is much smaller than L-drone, then we say that L-drone is equal to L effective. And that's what we will assume in this course mostly. You know, this is the same thing here. So you know, when you draw this, the transistor size, you can play with you know, this value. This value can be minimum, let's say 3 micron, but the W can be also 3 micron, the minimum one. But you know, we can play with W and L ratio. So as a designer, if you're a VLSI designer, you are free to choose this above the minimum value. Okay, so above the minimum value. The size, the minimum size is limited by the minimum feature size. And for digital circuits, typically the minimum length is used. Okay. So just to quickly maybe go through this. I mean, this is probably going to be the source, drain, and gate. Okay. So that's what we do. So in terms of the actual device, here, this is the drawing of the transistor, just cross-sectional view. Okay, so it's more convenient just to draw the cross-sectional view instead of the 3-dimensional view. But of course, you need to know that this extends like here, and then that's how the device is. Okay, and you know, of course, this is going to be also extended like this. The way that the device operates, you learned about this in your EE312 course. You know, you have seen this. So we will not go into details of that course, but this device here, I mean, here we will be considering this device as switch. Okay, so normally the switch is off. Okay, no current is flowing between source and drain if there is in the gate 0 volt. Okay, so okay, the current here, IDS, is going to be equal to 0. Okay. However, when we start applying a voltage, then there's going to be a leakage path here. Electrons will be attracted here. The holes will be repelled. So these electrons are going to create here a resistance path. And then depending on that resistance path, we will be able to pass current between drain and source. So if, let's say we have 5 volts here, drain, source, and the gate, okay? So here, the IDS is going to be larger than 0, okay? If the voltage V gate is larger than a certain value, let's say V threshold value, V gate, okay? So this is the device. So that's how we will consider this transistor. So if we have, let's say, you know, in order to make a gate, for example, we will be saying that this is now a resistor, and this is VDD, and this is our transistor model, I mean, or symbol, the MOS transistor. So here, if the input is 0, this is NMOS. NMOS is off, So that means IDS is equal to 0. That means V out is going to be equal to how much?
VDD.
VDD. Yes. So 0 volt output is VDD. So it's like good. It looks like it is an inverter. Okay. So if we apply a larger voltage here, let's say we apply here 5 volts, then this is going to be, let's say, 5 volts or VDD. So this is going to be on. So the you know, on means either it is in linear mode or sat mode, but that means IDS is going to be larger than 0. IDS is larger than 0. So V out is going to be, you know, depending on, you know, VDD minus IR or IDS times R. So if we select R, you know, large, and arrange this, V out is going to be low voltage. So we can quickly obtain an, you know, an inverter with this element nicely. And the nice thing about this here, this I gate is equal to 0. So remember, for the next gate in the BJT, you know, we need to have a current, but here we don't need such a current. So we can consider this element as if we have this. Okay, as a switch. Okay, so that's nice. Either it is off, so output will be high, or Vn is large, then output is going to be low. So here it looks like it's going to be 0, but there is going to be internal resistance here also. So some internal resistance of the transistor will prevent it to go all the way down to 0. Okay, but output is going to be low. So with the same concept, maybe we can make, you know, like this. I mean, one switch or another switch. So if we put 2 transistors like this, and then this is V out, then this is VDD, then this is going to be, you know, A input and B input. So what we obtain here is A dot B bar, okay, or NAND gates, okay. So this is very convenient, you know, that's the point here. This is a very convenient element for making digital circuits. We turn the switch on and off, okay. So I'm trying to get you into the feeling of how we can obtain digital circuits with NMOS transistors. So, you know, one other thing that we learned was CMOS. CMOS means complementary MOS technology, okay? So when we say CMOS, CMOS is a process technology. This is showing the process technology. I mean, you know, cross-sectional view of the device after this process. Okay. So here, the device, these devices are fabricated in a silicon wafer. Maybe the wafer thicknesses are about 500 micron, but the device that we implement here is maybe less than 5 micron. So maybe we should say that this is not to the scale. You know, the substrate and the device is formed just on top of 5 micron. Okay, so you know, that's kind of what we do. And again here, in order to implement the devices NMOS and PMOS, we need to use diffusions. And you know, so this one we have already seen how this is done, but then also we can implement PMOS transistors. Okay, so this is the NMOS, we call it, and then this device is, you know, PMOS transistor. So here, this is the cross-sectional view, and if you think about this device with the model or symbols, this is what it is going to be. Here is the bulk. This is VDD, that's what we do. And then we need to connect here to this NMOS, the layout wise, I mean, and this is going to be the substrate of this bulk. And then bulk is connected here, and then this is connected to ground, okay, ground path. So, you know, this two device, if they are connected later on, like here, and then we call this thing V in, and we call this thing V out, this is called CMOS inverter. We will be coming to this later on, okay, how to implement a CMOS inverter. But typically, instead of, you know, drawing this in that direction, you know, we do it this way. And this is going to be your CMOS device, CMOS inverter, V in, V out, where this is the PMOS, this is NMOS. Okay, so this is MN, this is MP device. Okay. So we need to maybe remember voltage current equations of these devices, but we will not spend too much time on this, you know, other than just remembering what they are. So in these devices, this is going to be the model of the NMOS transistor. And for the NMOS, this is drain, source, and gate. And there's this, what we call bulk, okay? So the bulk, typically we connect the bulk to source. And sometimes in the symbol for this device, we define it this way. But the symbol for the device changes from book to book, you know. We will be maybe talking, we need to talk about that. But the general idea is, you know, these operation modes. If the voltage, gate to source voltage is 0, output is going to be, or the current, drain to source current, drain to source current is going to be 0. But, you know, considering and coming back to this device, the device, starts, you start, initially, there is no leakage region here. So the current is going to be 0. Okay, but if we start applying here gate voltage larger than a certain voltage, there will be, we call it, there will be enough electrons here so that the channel is inverted. And that value of, channel, the value of the doping or electron concentration here, when it's equal to the doping of the substrate, that voltage, specific voltage, is defined as threshold voltage. So before threshold voltage also, we see that the current is going to be flowing between drain and source, but not significantly. It's negligible. Therefore, we say that when we gate to source voltage is less than the threshold of N, then IDS is going to be equal to 0. Okay, so here the real response of the transistor is like this. We gate to source, I drain to source. In fact, it goes like this, the response. Okay, so here we say that this specific voltage where the current starts really becoming realistic or so is called the threshold voltage, the threshold of N. I mean, here also there is slight current, but we ignore that. We say it is 0. And the nice thing about this device is that here I gate is always 0. Okay, so it doesn't require a voltage because of the, or current, because of the operation principle, right? I mean, we just create a field here. So this is silicon dioxide, dielectric, no current is passing. This is metal or polysilicon. Okay, so that's the cutoff mode of the transistor. And there are 2 other modes here. And the other modes are, linear mode. In the linear modes, we, the gate to source voltage, if it is larger than the threshold of N, but the drain to source voltage is less than the gate to source minus the threshold of N, then IDS is equal to, there's an equation here for the current, and that is going to be Kn the gate to source minus the threshold of N times VDS minus VDS squared divided by 2. Okay, so in fact, for very small values of for very small VDS values, okay, then this term can be ignored. And then we see that, therefore, IDS VDS relationship is going to be linear. That's why we call this thing linear region. And I guess you remember the voltage current equations here for these devices. But you know, this is what is obtained. Maybe I should erase this. So this will be starting linear, but then it starts deviating. We drain to source, I drain to source curves. Okay, so initially this is linear, but then after that, you know, this becomes more dominant, and that's what we have. So this region is called linear region. So beyond this fictitious point, it's linear region. Okay. So what is that fictitious point? The fictitious point, the drawing here is V drain to source is equal to V gate to source minus V threshold of N. So beyond that, this is going to be, I mean, when VDS is less than V gate to source minus V threshold voltage, then we call here linear region. So this region is the linear region. Again, the region is when this is smaller, okay? So what about when this is larger? So when this is larger means, maybe I should select this color, this region, okay? So VDS is larger than V gate to source minus V threshold of N. So when V gate to source again is larger than V threshold of N, and V drain to source is larger than V gate to source minus V threshold of N, then the current is going to be more stable in that mode. That's called saturation mode. And here, IDS current is calculated as Kn divided by 2 V gate to source minus V threshold of N square. And then that's a fixed value here maybe. But we notice that this thing slightly increases. Slightly increased amount is calculated from here. Okay, so when DS increases, it slightly increases also. Okay, so this is called channel length modulation effect or factor. Okay, it's lambda. So I'm quickly, you know, reminding you these operation thing here. If you want, you can look at your previous course data about this. We, you know, IDS, and then maybe up to here, and then after this comes like this. This is VTN and IDS versus VDS curves. This is V drain to source is equal to V gate to source minus V threshold of N. And here, maybe I can draw the curves here. This will be maybe this is what the curves are. So here is the line where V gate to source is less than V threshold of N is here. Okay. And then this is the saturation current for, let's say, 1 unit. Okay, V gate to source is equal to 2 volt, let's say. Let's say this is 1 volt. And then if you see a current here, and threshold voltage is 1 volt, let's say this current is, I don't know, 1 unit. 1 unit. And then this will be square of that, it goes like that. So this is going to be 4 units when the voltage is 3 volt. And the voltage is V gate to source is equal to 4 volts. This will be 9 units. Okay, so why? Because this current is related with V gate to source minus V threshold of N square is how IDS current is determined. Kn divided by 2, that's IDS. Okay, so this is drain, source, and gate. Okay, so the device here, you know, we talk about only the NMOSs, but I should talk about PMOS device also, and I should come to PMOS devices, and then maybe the model of that. I can maybe enter a page in between and show it to you. This is the enhancement transistor, but maybe I'm going to erase this here, and this device, later on we will be considering this device as a switch. Okay, drain, source, and gate. Either current or no current, but of course this is not like a pure switch. This is a nonlinear current characteristic switch. You know, we I should draw this separately. Maybe I'll talk about the PMOS device later on, or just talk about it here. So the enhancement transistor is the transistor where threshold needs to be, you know, larger than 0. But if you have, maybe this is N plus and N plus, and this is our transistor. So if you have already a channel is formed here, okay, doped, N minus doped, then it means that there's already a channel. So at 0 gate voltage, we have a current. So therefore, we need to give, you know, minus voltage to repel all those electrons in the channel so that we can turn off the device. So threshold voltage then is going to be negative. So the model or the symbol for this is showing that. So showing this, the channel here is how we represent, okay, or the transistor. So I will do, maybe I will show also the PMOS transistor here. Let me do that. I mean, for the PMOS transistor, the symbol is either like this. So we call this side source, this side drain, and this side bulk, and this is gate, okay? Or the symbol sometimes for VLSI designers or chip designers, we call this thing source, drain, and gate, okay? So we just put here the bubble because here we assume that this is going to be a switch, but the switch is working with the negative idea or reverse idea of the NMOS transistor. So that's the symbol, and the way that I look at the device is you know, I like to do this in order to find the same, or in order to remember similar equations. You know, instead of in the other one, let me do this maybe. Here, this current is I source to drain, okay? So in the let me do this. You know, in all others, we say for the NMOS. So let's say this is NMOS. For the NMOS, this was the symbol, and this is drain and source and gate. Okay. So here, when we say something like I source to drain, I drain to source, and then when we say we gate to source, we drain to source, we threshold of N. Okay, what else? Kn. Okay. For the PMOS, you need to do this. Maybe you know, for the PMOS, if you say this is source to drain, if you say this is the source to gate, and then we source to drain, and instead of this, if you take the threshold of P MOS transistor, and instead of this you say Kp, then all the equations are going to be valid. And then the I source to drain and V source to drain curves are going to be like this. This will be the fictitious thing. So here, you know, what was this one? Drain to source, right? So we need to say V source to drain is equal to V source to gate minus VTP, okay? So if this is the case, then, you know, the lines are going to be again like this, and then this is going to be like that. So here, this line is when we source to gate is less than V threshold of P. This one is V source to gate is, let's say, is equal to 2 volts. which is 1 volt. So inside is -1. Okay, absolute value of it. So then this one is going to be source to gate is equal to 3 volt or 4 volts. Okay. So then the equations are going to be also very similar. So cutoff means V source to gate is less than VTP. And if this is the case, I source to drain is going to be equal to 0. Okay. So what about the linear mode? Linear mode means we source to gate is larger than VTP, and for this case I source to drain is going to be equal to KP times V source to gate minus VTP V source to drain minus V source to drain square divided by 2. Okay, every equation that you learned or memorized will be valid. But there is also one more case here, right? So I should have written this maybe differently. Not only this, for the linear mode, V source to gate should be larger than VTP, and V source to drain should be larger than less than V source to gate minus VTP, absolute value. So if this is the case, then you will have this current. So for the SAT mode, to happen, V source to gate is larger than VTP, and V source to drain should be larger than V source to gate minus VTP. And if this is the case, I source to drain current is going to be equal to KP divided by 2 V source to gate minus V threshold of P, absolute value of this, square times maybe 1 plus lambda V source to drain. Okay. So I'm just quickly going through these to show you what the device is, or remind you. Okay. But the convention, the most important thing here is to use this convention, because if you use this convention, your life will be easier. Okay. So please, instead of source to drain to source, source to drain, and then that kind of convention, this is going to be for NMOS. This is going to be for PMOS. Okay. So shall we give a break or continue a little bit more and then stop for today? What do you say?
Hocam bence
Buyurun
hocam.
Söyle, dinliyorum.
Mola biraz daha iyi olabilir hocam da bu benim fikrim. Yani blok yapalım diyen de olabilir, o yüzden bir şey diyemeyeceğim.
Neyse, bir 10 dakika mola verelim. Şey yapalım. 50'de mi buluşacağız? Bence biraz bunun üzerinden devam edelim ya. Bakayım, yoksa konsepti mi anlatacağız? Evet. Tamam, bir mola verelim hadi. Okey. Şimdi kapatayım ben. Stops this one. Okay, so we reviewed the element here. Typically, we can make an inverter very simply, with this device. So I guess I already mentioned about making an inverter like this. Okay, or like here, it's given, right? So, if the input is 0, this is off, and IDS is equal to 0, so output is going to be VDD. Okay, so that's going to be your V output high voltage. So if we decide to put maybe 5 volt here, then this is going to be, in fact, it's going to be in linear mode. We know that. And then IDS will be larger than 0. And then V out will be low voltage, V output low, which will be less than, we prefer this to be less than threshold voltage so that it will be assumed to be low. Okay, so this is an inverter. But this thing here is difficult to implement in IC technology. So in general, we need a load here. And that load can be resistor, but it is difficult to implement in IC technology. Instead, we use here some maybe active elements, okay? I mean, non-linear resistances, for example, we can call this, okay? So either we will be putting another NMOS transistor here as the load, or we can put a depletion type transistor or enhancement transistor, okay? So in the coming slides, we will be first learning about this one, how we can obtain voltage transfer curve, and then how we can determine output high, output low, and other values. Okay. So let's start doing this for the resistive load one, and see how the curves are going to be appearing. So here, we can look at the extreme cases. So let's say one case is where V in is less than the threshold voltage of N. Let's say this is 1 volt, okay? So if this is the case, we know that NMOS Mn is off. If this is off, then IDS is equal to 0. If that's the case, then V out is going to be VDD. I mean, if that's the case, V out, which is equal to VDD minus IDS times RL, is going to be equal to VDD. So this is valid up to here, V threshold of N. So this is going to be our really output voltage. This is case one. So notice that V out is equal to VDS. So V out is equal to VDS. So initially, let's say slightly larger than here. Okay, threshold voltage. Let's say this is V threshold of N is equal to 1 volt. Okay, so this is 1 volt. And we gate to source for the case 2. We gate to source, let's say, is slightly larger. I mean, 1.1 volt. If that's the case, then the transistor is going to have IDS is going to be larger than, slightly larger than 0. Therefore, output V out will be VDD minus slightly small, small voltage on RL. So therefore, here we drain to source, which is like maybe 4.5 volt, okay, 4.5 volts, let's say. Okay, is going to be larger than V gate to source minus V threshold voltage, which is 1.1 volt minus 1 volt. So this is about 0.1 volt, okay? So basically, transistor in 2, cycle 2, MN will be in SAT mode initially. Okay, so the current will start, the voltage will start dropping in the second mode. So this will be decreasing, okay? And the decreasing is going to be for a while, maybe it's going to be sharp. And then the decreasing will decrease. Decreasing amount will decrease, okay? So because after a while, so this is, let's say 2, transistor will go into linear region, okay? So somewhere around here, transistor will go into linear region, okay? Vx or the input output is not related with that, no. Okay. So eventually there's going to be a voltage here which will be related to VDD. Remember, VDD was V output high. So the value of V output high, that's corresponding to input. If the input is V output high, this value will be called V output low. So that's going to be, you know, your response, basically. Okay. In the SAT mode, V out, how the V out is going to change? V out is going to change with VDD minus RL times IDS. In the SAT mode, what is IDS? Kn divided by 2 V gate to source minus V threshold of N square. And what is this value? V in. So V in and V out. Okay, so relationship of V in and V out is going to be nonlinear. Okay. So, and for the last case, the value, since the transistor is going to be in the, let me maybe calculate it like this. In the third case here, for the third case, Mn is going to be in linear mode. So V out will be equal to VDD minus RL times Kn. V gate to source is V in minus V threshold of N. V drain to source is V out. And then minus V out square divided by 2. So V in, V out graphic is going to be like this. Okay, so what is the value of when V in is equal to the extreme case VDD, which is V output high, then I can calculate here V out. That V out, which will be called V output low, can be calculated. And here, while trying to calculate this, maybe we can ignore, because we know that it will be a low value, something smaller than 1 volt. So maybe it's 0.5 volt, okay? So therefore, that last item can, I mean, either you can solve this thing, V in, V out graphic equation, or roughly you can say that this will be VDD divided by 1 plus Kn RL VDD minus V threshold of N. Okay, so this will be maybe about 0.5 volt, preferably, or so. Okay, so in any case, this will work like an inverter, but our definitions are not going to be valid. I mean, and the breakpoints are going to be a little bit, maybe, what is V input high, V input low? We will say that slope -1 and slope -1 points are defined as V input low, and this will be called as V input high. Okay, so I guess I'm going to stop here, but we can obtain the same graph maybe from the the same graph can be obtained from graphical analysis. Let me do that also quickly. You know, if we look at the IDS VDS graph, we said that this will be something like this: 1, 4, 9, and 16. Okay, this will be 16. This will be, you know, related with ratioed with 9. This is ratioed with 4, and this will be ratioed with 1. Okay, so this is V gate to source is equal to 2. This is 3, 4, and 5 volt. And this will be the curve for V in VDS. So VDS is V out and then IDS. Okay, so we know that we also have a relationship here of the device here. This current IRL is also equal to IDS, and this V out is here. So I also have a graphic here, VDD minus V out divided by or this one, VDD minus V out is equal to IDS times RL. So and IDS is equal to IRL. So I mean, if you look at that, there is also an interesting relationship between this current and then V out. And so that relationship is like this: when V out is equal to 0, IDS is equal to VDD divided by RL. So here, I don't know where it corresponds to, but somewhere around here, let's say. Okay, so this one is VDD divided by RL. So the other extreme is when IDS is equal to 0, V out will be equal to VDD. Okay, so that's here, VDD. So in fact, we have a load line here, basically. Okay, so this will be our relationship. So the cross-sectional points here are going to be our solutions. So this is mean is equal or less than 1 volt, which is the threshold of N. So from here also I can quickly draw V in, V out graph. How input less than 1 is the solution is here. So let me select a different color here. Nice color here. So this will be one of the solution points. Let's call this is A. So if input is less than the threshold voltage, VTN, output will be VDD. Okay. So let's go to maybe second region here, this point. So this is 2 volt. So this was 1 volt. Okay. For 2 volt, what is the output here? Maybe, I don't know, VB. So we select for the 2 volt corresponding voltage, VB. So that's going to be another solution. And then another one is going to be maybe this one, VC. So this is C point. So for 3 volts, output is going to be, oh, that's maybe here. Okay, VC. So after that, maybe I select this one. This is D. And this one, D is going to be here for 4 volts. It is here. Okay, VD. And then for 5 volts, let me select this brown. I don't know, for 5 volts, the output cross-section point is E, and that value is here, less than 1 volt. So that's going to be E. So as you see here, we can connect them all and then get a voltage real response of this device. So I couldn't match it nicely, but I guess you got the idea. You got the idea, I hope. So that's going to be the curve that you obtain from load line analysis, okay? So I guess I'm going to stop here. And next time we will be looking at this a little bit more. And then we will be looking at the other cases for the load. Okay? So I'm stopping you.
Hocam, midterm hakkında bir şey
Dinliyorum.
soracaktım ama nereye kadar olacak? Bir de nasıl olacak? Optical üzerinden, yani klasik sorular mı? PDF mi?